Hello everyone, so I'm Richard, I'm the co-founder of Naptha AI, and today I'm going to talk a little bit about the multi-agent approach to AGI, which is something that you may not have heard of before. And I think the reason for this is that we tend to have this worldview that AGI is going to be a single entity, which is put forward by the big labs. And this has a lot of implications for things like AI safety, because, what happens if the one AGI, the godlike entity, goes rogue? You're kind of screwed. But I tend to think that AGI is much more likely to be a network of entities or a society or an ecology of entities. And this fits much more with the multi-agent approach that is becoming popular in the AI space. Just for fun, in case you're interested in learning more about AGI as a godlike entity versus AGI as an ecology, inspired by animism, I recently wrote a blog post that explores this from a kind of philosophical perspective. So check that out. I'll put a link in the description below. Okay, so I'm going to go through three different generations of scaling that, some of them you will be familiar with and some that are perhaps new to you. But the first generation was basically scale is all you need. So as recently as a year ago, all of the big labs were basically saying that all we need to do to get to AGI is to scale bigger and bigger models. And then in April, Sam Altman came out and said, the era of scaling these giant AI models is already over. So we're still seeing benefits from training these bigger models, but those benefits are diminishing and we need new approaches to get to AGI. So with the recent release of GPT 4.5, this became really clear. I don't know if any of you have played around with this, but it may be better, but it's also subtle, right? And GPT 4.5 used, I think, 10x more compute than GPT 4. And for the benefits to be subtle, it's very easy to see that, training bigger and bigger models is not going to get us to AGI. The next generation of scaling that we saw was in scaling inference time compute. So this became mainstream with the launch of the O1 series of models with OpenAI. People in the AI space, the builders, have been familiar with approaches like this since, 2022, as early as that, with, frameworks like LangChain, for example, where people were doing chain of thought prompting, different prompt chaining. All that sort of stuff is in the style of scaling inference time compute. What it basically means is that rather than making a single call to a model, you make many calls to a model, which could be in a chain, like I mentioned, or they could be in parallel, and then you do some sort of averaging, majority voting to combine the answers. And that's basically what the O1 model does, along with the O3 model, and also some more open source examples like DeepSeek R1, for example. There are still some issues with scaling inference time compute. I don't know if any of you have used deep research by Google or ChatGPT, for example, but it does tend to hallucinate, research that doesn't overlap with the original content. So there are still issues with this approach, and I think that's something that this next generation that I'm about to talk of can solve. So what is the third generation? This is what I'm calling multi-agent scaling. So the question here is there a predictable relationship between agent scale and performance? So in the previous graph for the second generation, what we saw was scaling the number of model calls and doing some sort of averaging increases the performance. But all of those calls are to the same model. So for example, for O1, all of those calls might be to, GPT-4 or something like that. And what the multi-agent approach proposes is that rather than making all of these calls to the same model, we can actually make calls to different models, right? And there's a few different papers that have come out that are starting to explore this. For example, there's the More Agents is All You Need paper, which scales up to, I think, about 25 different agents and basically just does majority voting on the outputs. And then there's a more recent paper called Scaling Large Language Model Based Multi-Agent Collaboration, which scales up to, I think, over 1,000 agents and sees performance benefits. So the performance does improve for that second paper up to about 1,000 agents, but then it starts to level off. You can kind of see this in the graph in the bottom right. And this is for a number of reasons. It's hard to figure out what the communication pattern should be between these different agents. They tried a number of different patterns. The one that I'm showing in the graph is for random, but they also did other patterns as well. I think for all of them, they basically saw the benefits start to level off. But this generation isn't in the mainstream yet. People are still talking a lot about test time compute with the same model. I think, maybe if 2025 is the year of agents, 2026 is going to be the year of multi-agent systems. And we're going to start to see people talk much more about multi-agent scaling rather than, test time scaling of a single model. So why does making many calls to different models improve performance? The answer is diversity or heterogeneity. So there's a lot of different dimensions that you can use diversity for to improve performance. For example, one of them is just in using different models, as I mentioned. So ensembles of models have always performed better than single models. You might remember this from the days of Kaggle, for example. Kaggle is this competition platform where they would, allow entries from different people training models. And what would usually happen is that an ensemble would always win. So maybe you train a machine learning model, you train a random forest, you train like a third type of model, and then you basically just average the outputs of those, and that always performs better than any one single model. Well, we see the same thing with LLMs. One of the first papers to show this was, the mixture of agents paper. I think in that paper, what they did was they had 8 different agents, and they showed that 8 agents using the same underlying model performs less well than 8 agents using 8 different models. And that's even true when, the single model that you use is the most powerful one, which was, maybe GPT 3.5 or 4 at the time. And then using the 8 different models, they used less performant models that were, open source. And even then, it performed better than the single model. So basically, increasing the diversity of models that you use in multi-agent systems has been shown to increase performance. The other thing that you can do is increase diversity of architectures. So there's this paper called Internet of Agents, and what they showed is that if you have architectures that are different within a multi-agent system, you will also improve performance. So maybe one of the agent uses a cognitive architecture, for example, and maybe another agent uses like a different type of loop and some sort of logic in that loop. The more different the types of architectures that you use in your multi-agent systems, and the more of them that you have, the better the performance of the overall system. That paper also showed that diversity of local knowledge improves performance. This is kind of intuitive. If you have a lot of different agents working with different local knowledge bases, they're going to perform better. Diversity of data has always been something that improves performance. We know that. And that paper also found that increasing the diversity of tools that are accessed by the agents also improves performance. So basically just increasing diversity or heterogeneity in all of these different dimensions improves performance. And that's why, for example, in the previous slide, when we scale multi-agent systems that have different models, we actually improve performance. And an intuitive reason for that is that, if one model generates an output and we generate another output with the same model, both of those outputs will be, subject to the same failure modes, because maybe that model has a blind spot or something like that. Whereas if we use many different models, then different models can account for the different failure modes or blind spots of different of the other models and average out to a certain extent. So diversity improves performance, and this is a big benefit of multi-agent systems over the kind of single agent or single model approach. The challenge is that it's very difficult for researchers and engineers to build this multi-agent type of AI. So there's many reasons for this. Let's say you want to use a lot of different models in a multi-agent system. You also need to do tool calling with all of those models, because that's a really important feature for agents. And even doing tool calling with different models is actually difficult, because different models have different standards and formats for tool calling. For example, the Noose Hermes models, when they want to do a tool call, they output text in XML tags. Whereas if Mistral wants to do a tool call, it outputs these kind of like square brackets with tool call in capital letters. So if you're an AI engineer, what you end up needing to do is to write a lot of custom parsers to parse these tool calls from the outputs so that you can, call that tool. And if you want to do that for 100 models, 1,000 models, obviously that doesn't scale and gets really difficult. So that's one issue, tool calling with many different open source models. Another challenge is that structured output really varies across different models. So often if you're building an app, you will want your model to output some sort of structured format like JSON, for example, so that you can parse the different fields in that JSON. And depending on which model you're using, it's going to be more or less good at adhering to these structured outputs. So smaller models, of course, tend to be not as good. But also in different models, maybe you need to like prompt in a different way. Maybe you need to beg it a little bit more. This often varies model to model. And of course, this is work that AI engineers end up having to do if you're using many different models. There's also other approaches, like you can use, is it outlines, the library for using an FSM to enforce structured output. So, maybe you use that with some of the models that don't work as well with prompting. Maybe you have different approaches for different models. And this is something that adds a lot of complexity. And then we get on to, reasoning. So whatever about tool calling, not having standards, we're even earlier in, having access to open source reasoning models, and different models will output different, thought processes, different chains of thought with different formats. Maybe some of them say step 1, step 2, step 3. Maybe some others use like XML tags. Maybe different formats are used all around. So that makes it really, really hard to build with many different open source reasoning models. So whatever about tool calling standards not having solidified, reasoning standards are even earlier. There's also very few standards for agent interactions. So like, how should an agent request a task from another agent? There's been a few protocols that have proposed things here. People might remember the agent protocol, which was proposed by the AI Engineering Foundation. That was basically a REST API that proposes that each agent has an endpoint for like creating tasks, for updating tasks, and things like that. I don't think the AI Engineering Foundation is active anymore, but that was a really good step in the right direction. And there's even quite a bit of work from the 80s in the AI space that tried to create standards for agents to interact. Back in the 80s, that was the expert systems era of AI, and they thought that AI was about to start doing a lot of useful work, so they created all of these standards. There was this organization called FIPA, which was like Foundation for Physical Agents or something, that started to create a lot of these standards, and they invented this thing called the Agent Communication Language, the ACL, which is like just a bunch of different protocols for agents to interact. One of those is called Contract Net Protocol, for example, which I tend to describe as something like the Upwork protocol. So it's a way for agents to, contract with other agents. So step 1 of Contract Net Protocol would be for one agent that wants a task to be done to put out something like an RFP, a request for proposals, from other agents, and, specify what it wants done. Then other agents will bid on that RFP with, a price proposed and that sort of thing. A bunch of agents will submit proposals. Then the agents that is requesting the proposals will, take a look at them and vet them and choose one. That agent will then go and do the work, submit the work, and then that work will be approved or rejected. So this is an example of a standard from the 80s that we could use with agent interactions now. Agents requesting tasks from other agents is a really useful thing. And so we need to really develop these further. The other issue is that like multi-agent systems, the frameworks built by different researchers don't really interoperate. So how I tend to describe this is that is with respect to Hugging Face transformers and the issues that researchers used to have. So I don't know if anyone remembers pre-Hugging Face transformers, but a lot of researchers were working on transformers. And the issue was that if one research group created, some sort of new layer for a transformer or something like that, because they all wrote their transformer frameworks from scratch, it meant that that new layer wasn't automatically usable by all of the different researchers. And what Hugging Face did was they created the Hugging Face Transformers library, which kind of standardized the way that researchers build transformers. And what that meant is that if one group created a new layer, then that was automatically usable by all of the other groups. So it unlocked these network effects. With multi-agent system frameworks, what I tend to say to people is that we're in the pre-Hugging Face transformers era, where a lot of people are working on, agents, multi-agent systems, different types of memory, but none of it interoperates. And so if one new group creates a new memory module, for example, that isn't automatically usable by all of the other groups. And so what we need are something like Hugging Face transformers, but for multi-agent systems. And I think it will look a little bit different to Hugging Face transformers. I don't think everyone is going to use the same multi-agent system library. We've already seen like everyone developing their own library essentially. But so I think people can continue to build their own multi-agent system frameworks, but we need some sort of like standards for interoperability between those. And that's something that, Naptha is working on with Naptha modules. Just to mention that, my observations are shared by other people. In the bottom right, you'll see a picture of these Google executives who developed Android, who think a new operating system is needed to fully realize the potential of AI agents. This is essentially what Naptha has been proposing for a few years now. We need a platform for these multi-agent systems to run on, like an operating system. And what an operating system does is it creates certain standards for different entities within that system to interact. So there's other groups that are working on this now as well. Okay, so I'm just going to very quickly talk about some of the components in the Naptha stack and how it ties in with some of the stuff that we've talked about so far. So what is Naptha? Naptha is a framework and infrastructure for building multi-agent systems at scale with diverse or heterogeneous models, architecture, and data. So we really believe in this multi-agent approach to AGI, and we want to make it easier for builders to build within this approach. So we want to make it easy for them to use many models, many architectures, a lot of local data with their agents. And we also want them to be able to scale up to millions of agents within these multi-agent systems. So one of the ways that we support builders to do that is through Naptha nodes. Naptha nodes are like the infrastructure. It's basically like an ML ops platform for running these multi-agent systems. So the Naptha node provides a bunch of components. It packages them together and makes it really easy for builders to run agents locally and for those agents to interact with other agents on the network. So one of the parts of the Naptha node is this local inference. So we support Ollama for laptops or VLLM if you have a GPU. And we've standardized, the tool calling for about 16 open source models. And what that means is that you as a builder will find it easier to build on top of the Naptha node if you want to use 16 different models with tool calling with your multi-agent systems. We've also worked on standardizing structured output across all of these different models as well. We can use different approaches for different models. And also we're starting to work on standardizing reasoning across these models as we work towards supporting multi-agent reasoning. The other thing that Naptha nodes provide is local databases for local storage of knowledge and memory. So we use Postgres. There's like a Postgres Vector DB as well. Whatever agents are running on your Naptha nodes can very easily store knowledge and memory within the local database. And we also, solve for communication with with agents running on different devices. We support 3 different communication protocols at the moment: HTTP, WebSockets, and gRPC. And that scales as well. And finally, we do a lot of orchestration within the Naptha node using things like task queues, Celery for Python, RabbitMQ, and workers, so that you can run many agents on a single node. So that's the Naptha nodes. Then what are Naptha modules? So I mentioned before that multi-agent frameworks don't really interoperate. The idea behind the Naptha module is to make it easier for all of these different agent frameworks to interoperate. You can kind of think of it like a very thin wrapper around your agent that provides this standard interface, allowing it to interact with agents within other frameworks. So Naptha modules are designed to be framework agnostic. You can build a Naptha module with any existing framework that you're using, like LangChain or Crew AI or Pydantic AI, for example. It's basically just like a poetry package, or it's also a little bit like an MCP server, which I'll come back to it in a minute. But basically you can just onboard your agent from any framework and implement it as a Naptha module. And what that allows is your agent to interact with other agents that have been created as Naptha modules. We're also working on decorators to automate this conversion into Naptha modules. So the idea is that you can build your agent in, for example, LangChain or Crew AI. You can import the Naptha SDK. You can just add a decorator above your agent class or your orchestrator class, for example, and it will automatically create this package, this module for you. So that works for Crew AI currently. We also just got it working for Camel AI and for LangChain, and we'll be launching that soon. And Naptha modules don't just support agents. There's other types of Naptha modules as well, like there's orchestrators, for example, orchestrator modules, tool modules, memory modules, environment modules. All of these modules are basically just like poetry packages with a few extras. But what it means is that, orchestrators built using different frameworks can interact, tools using different frameworks can interact. and environments, which are, for doing RL with agents. You can onboard those from different frameworks like, Google Concordia, for example. Okay, so just to touch very quickly on MCP. So I was at the AI Engineering Summit recently at the Anthropic workshop where they talked about MCP, and MCP is getting a lot of traction online, and with Naptha we really want to tap into that and help to grow that by fully supporting MCP. So MCP is the Model Context Protocol. What it allows you to do is to for your LLM running in a client like the Anthropic desktop or Cursor, for example, to make use of tools that may be on like local servers or external servers. And Naptha has supported this for quite a long time. So with Naptha, you can kind of see in the image below, you can have an agent running locally, and that can make a call to a tool server running on a different device. So we've supported something like MCP for quite a while, but what we want to do now is fully support the MCP, and we have a request for comments, a document in our community that aims to do that. And we actually go even further than just supporting tools. As I mentioned, we support many other things like knowledge bases, environments, orchestrators, and we hope that we can actually expand on MCP by supporting more than just tools, but also supporting interactions with other agents and knowledge bases and things like that. For anyone who was at the Anthropic workshop, there was actually a slide of this where he talked about the direction that he wants MCP to go is to enable these multi-agent systems to interact. And I think he had a diagram of an orchestrator agent with 3 other agents, and each of those was an MCP server and a client. Naptha can kind of already do this. We can already have an orchestrator running on one node with an agent on another, making a call to a tool on another. It's just that it's not fully MCP compatible yet. But our plan is to, in the next week or two, fully support MCP to enable these use cases like in the Anthropic workshop. Okay, just to start wrapping up. So, I've talked a lot about the multi-agent approach to AGI. We think it can be more performant. As I mentioned, we think it's going to scale better. I talked a little bit about that as well. I also think it's safer. And I touched on this already by saying, what happens if one AGI goes rogue? Well, you're kind of screwed. Whereas, if you think of AGI as a multi-agent system, the safety implications are much different. So what happens if an AGI, if one entity goes rogue in a multi-agent system? It doesn't really matter because, the other agents in that system can account for it. And this is really how the world works, right? We have a lot of rogue agents in this world, but, it just so happens that there's more good agents than bad agents that can counteract the bad agents in the system. One of the other reasons that I'm so excited about the multi-agent approach to AGI is that, probably the hardest challenge with multi-agent AGI is, the coordination between these different entities. So I showed the graph of like only being able to scale up to 1,000 entities. One of the reasons that the performance drops off is because we don't really know how those agents within that 1,000 multi-agent system should coordinate. So a lot of the challenges that we need to face are around coordination in these multi-agent systems. And in my opinion, a lot of the biggest problems that we face in the world today in humans are related to coordination. How do we coordinate our society better? How do we coordinate to solve climate change? How do we coordinate pandemic responses better? A lot of the biggest problems that we face are coordination. So by understanding multi-agent systems and how agents coordinate within these systems, hopefully we can turn that around on ourselves and improve the coordinations of humans in the world. So I really think that multi-agent AGI is a really promising approach, not just for the AI space, but for society in general. Okay. So if you liked this, we're hiring for a bunch of roles at the moment across many different skill sets. So, I touched on this a little bit, but to build multi-agent AGI, we need a lot of people that are working on coordination. And that includes things like people like social scientists, game theorists, economists. All of this becomes much more important when it comes to multi-agent AGI. And they're not so much important in single AGI. You don't need, if you just have a single entity as AGI, there's no game to play because there's only one player, right? There's no economy, there's no society. So I think this approach is really interesting for people with these different skill sets. And of course, we still need a bunch of AI researchers to coordinate with social scientists, game theorists, and economists. So if you're interested, please reach out to team@naptha.ai. We'd love to chat to you. And yeah, I hope you enjoyed the talk, and I hope to create more content on this in future. This was kind of an experimental video to see how much people like this type of content, and I'm hoping to create more. So yeah, please subscribe, send me a message if you enjoyed it, and yeah, reach out if you're interested in working with us. Thanks, everyone.